So here's my second attempt for proving the perpendicular bisector theorem for circles. The theorem says that the perpendicular bisector of a chord must pass through the circle center, and that's when you have a chord passing through the circle touching each end, and you draw a line that's perpendicular to the chord and that divides the chord into two equal parts. That's why the line is called the perpendicular bisector of the chord. If you want to see the first proof, I've attached a link to it in the description and in the comments section. This is the video thumbnail, so you can check it out after this video if you wish. So let's show that when this perpendicular line bisects any chord in a circle, it must pass through the center of the circle. Be aware that I'm only going to be discussing lines that are perpendicular to the chord, such as the one we see here. And here's another example. This is also perpendicular to the chord, and we're attempting to show that only the one that bisects the chord passes through the center of the circle, and that means we're going to exclude any lines that are not perpendicular to the chord. For example, this line, that's clearly not perpendicular, or a line like this, obviously that's not perpendicular either. So these types of lines can be disregarded when dealing with the theorem. So let's begin showing why this theorem is true. We have 3 points of interest here. We have the circle center and a chord, each end of which touches the edge of the circle. I'm now going to draw a line from each end of the chord to the circle's center. The two lines are joined at the center of the circle. Since both of these lines start at the circle's edge and end at the circle's center, they must be the length of the radius. They must both be the same length, and I'm going to give the length a label of r for each one. And now, given that these two lines we just drew are joined at the center of the circle, and the other end of each of these lines is joined to one of the ends of the chord, this has formed a triangle, where the left and right edges are the length of the radius, and the base of the triangle is the chord. So the triangle has two edges of the same length, and we know that is a definition of an isosceles triangle. The base is unique, and then the other two edges are of the same length. Now, an additional thing to notice here is that the vertex that's opposite the base in this triangle is exactly at the circle center, because that's where the two edges are joined. Now I'm going to add a line which is perpendicular to the base and passes through the vertex that's opposite the base. Now, when a line like this that is perpendicular to the base passes through the opposite vertex in an isosceles triangle, it also has another very specific property. It must also divide the base into two equal parts, which means that in this triangle, the left side of the base and the right side of the base have the same value. Let's give them both the value of length b. But the base of this triangle is really just the original chord. The line that we've drawn has bisected the chord. The line was perpendicular to the chord, so it is a perpendicular bisector, and because it passes through the vertex that's opposite the base, and that vertex is just the center of the circle, the perpendicular bisector of the chord passes through the circle center. Now, do any other lines perpendicular to the chord pass through the center? Well, let's bring in an example we used earlier. Well, the line is perpendicular, but if we focus just on the perpendicular and the isosceles triangle, the line is perpendicular to the base, but doesn't pass through the vertex that's opposite the base, which means that it does not divide the base into two equal parts, and so it is not a perpendicular bisector. But the base of the triangle is just the chord in a circle, and so this perpendicular line is not a perpendicular bisector of the chord, and clearly it does not pass through the circle's center. The only perpendicular line that can pass through the center of the circle must be the same line that is perpendicular to the base of the isosceles triangle and passes through the vertex that's opposite the base, because the vertex that's opposite the base in the isosceles triangle is at the same point as the circle center. And we already saw that the only line that's perpendicular to the base in a triangle and that passes through the vertex opposite the base is the one that's a perpendicular bisector of the base, and the perpendicular bisector of the base is really the perpendicular bisector of the chord. So the line that's perpendicular to the chord and that passes through the circle center must be the perpendicular bisector of the chord. And since there are no other positions where the perpendicular bisector could be, it must pass through the circle center, and that's exactly what the theorem states. The perpendicular bisector of the chord must pass through the circle center. If you'd like to know a little bit more about why the perpendicular bisector of the base in an isosceles triangle must pass through the vertex opposite the base, feel free to check out an earlier video I did explaining why this must be the case. I've linked that in the description as well, and also in the comment section. That's it for now. Thanks for watching.